Good morning, students. In the last class, we had seen Faraday's and Lenge's law, and we had also defined the magnetic flux. Now, we shall today study a topic, motional EMF. So, we shall find out what is motional EMF and we shall derive an expression for motional EMF. To study motional EMF, we need certain points which we studied last time. So the first point was regarding the magnetic flux. So magnetic flux is given by the product of magnetic field and area when the field is perpendicular to the surface. Suppose this is a surface and you have a magnetic field acting perpendicular to it. So whenever the magnetic field is perpendicular to a given surface, the flux through it is maximum, and we had seen that it is given by B into A, product of magnetic field and area of the surface. Also, when the magnetic flux changes with time, that is you have d phi B upon dt, rate of change of magnetic flux. So whenever there is change in magnetic flux, an EMF is induced in the circuit, and the induced EMF according to Faraday's law is given by E is equals to minus d phi B upon dt. So these two equations we will be today using for the derivation of motional EMF. Now, just now I told you, whenever there is change in magnetic flux, EMF is induced. Such EMF induced in a straight conductor, we call it as motional EMF. So, whenever EMF is induced in a straight conductor, flux should change it. Flux associated with it should change. So, how is it possible? For that, the conductor is made to move in the magnetic field in a perpendicular direction. That is, whenever the conductor moves in a magnetic field perpendicular to it, then flux linked with it changes, and therefore EMF is induced in it, and that EMF is called as motional EMF. So what is the actual definition of motional EMF? I have written it here. It is the EMF induced in a straight conductor when it moves perpendicular to the magnetic field. So that EMF induced in the straight conductor, we call it as the motional EMF. Now let us try to derive an equation for motional EMF. The figure required is very simple. I have drawn the figure here. All over the figure I have put cross marks. What do these cross marks indicate? They indicate a magnetic field which is perpendicular to the plane of the paper and it is directed inwards. So you consider that there is a normal magnetic field, then that normal magnetic field I have denoted all over by the cross marks. Now in this magnetic field, we are having a metallic frame, rectangular in shape, that is ABCD. So this ABCD is a rectangular metal frame which is placed in this magnetic field. Now on this metal frame, let us keep our straight conductor PQ. Let us say length of the conductor is L and it is at a distance x from the side CD. So we have kept a straight conductor on the metallic frame. Now our aim is to find out what is the EMF induced in this straight conductor when it moves perpendicular to the magnetic field. Now let us find out the loop PQCD. You can see this loop PQCD. So first we shall find out what is the area of the loop PQCD. So this is a rectangular in shape. Therefore area will be nothing but length into breadth. So it will be the product of L into X. So the area of the loop PQCD is given as L into X. Now how is the direction of the magnetic field? This loop is in the plane of the board and the magnetic field is perpendicular to it. So whenever the field is perpendicular to the surface, the flux through it is given by the product of magnetic field and area. So the flux through this given loop is given as B into area. So put the value of area. Area is nothing but Lx. So what is the flux through this loop? That is B into Lx. Now this is the magnetic flux linked with this PQCD loop. Now when is the magnetic flux going to change? If the magnetic flux changes, then only EMF will be induced. So if you want to change the magnetic flux, what is done? The straight conductor PQ moves towards the left with a velocity v. So when the conductor moves in the magnetic field, what happens? The flux linked with it changes, and whenever the flux changes, what is induced in the conductor? An EMF is induced in the conductor. So here, let us find out the EMF induced. So it is given by Faraday's law as minus d phi b upon dt. Put the value of phi b. What is phi b? B into Lx. Now in this equation, B and L are constants. You can take them outside. So minus BL into dx upon dt. Now what is dx upon dt? Dx upon dt is nothing but rate of change of displacement. So this you have learnt last year. Velocity is defined as rate of change of displacement. So velocity of the conductor V is nothing but dx upon dt. Also it is with a negative sign. Why a negative sign is used? Because as time passes, x goes on decreasing. So x decreases with time, therefore velocity is written with a negative sign. So for this minus dx upon dt, let us put it as v. Therefore the induced EMF becomes equals to BLV. So what are the various terms in this equation? B is the magnetic field, L is length of the conductor, V is velocity of the conductor. So this is nothing but an expression for motional EMF. So what are the questions? How are the questions asked on this? First question will be for 1 mark, what is motional EMF? And another question will be derive an expression for motional EMF. This is asked frequently for 3 marks. So first question, let us revise again. What is motional EMF? It is the EMF induced in a straight conductor when it moves perpendicular to the magnetic field. And how to derive an expression for motional EMF? What are the steps? First draw this figure. So PQ is our conductor of length L moving with a velocity V. Take the rectangular loop PQCD. First find out the area of this loop, then find out flux through this loop, and then find out the induced EMF. According to Faraday's law, it is minus d phi b upon dt. Put the value of phi b and simplify. You will get the value as E is equals to BLV. So this is an expression for motional EMF. So you learn the derivation thoroughly because it is important from your exam point of view. So these are the 2 points regarding the motional EMF. Now the next point we shall discuss is, we shall discuss about eddy currents. These eddy currents were discovered by the physicist Foucault, so they are also called as Foucault currents. So before going to eddy currents, let us recall the coil and magnet experiment of Faraday. So the experiment which we had discussed was like this. A coil was connected to a galvanometer. A magnet was either moved towards the coil or it was moved away from the coil. So whenever you move a magnet towards or away from the coil, the magnetic flux linked with the coil changes and EMF is induced in it. A current begins to flow in the circuit. That we call it as a induced current. Now, this induced current flows from one terminal to another. This is a normal induced current. Now suppose, let us replace the coil by a very thick metallic conductor, like a metal block you take. So if the coil is replaced by a thick metal block like this, this is a metal block, this is the thickness of the block. Let us take a thick metal block or a thick metal plate. So if you have a thick conductor like this, thick metallic conductor, then what about the induced current? Can you induce current in this thick metal plate? You can induce current in the thick metal plate by changing the magnetic flux with it. So when you induce current in a thick metal plate by changing the magnetic flux, the current induced are circular currents like this. Circular currents are induced here. These are normal currents flowing from one terminal to another. Whereas in the thick conductor, it is found that the electrons in the conductor revolve round and round. So currents are in the form of these closed paths. So these are called as the circulating currents. So that is why the name eddy currents is given to it. The name eddy is given because you know the meaning of the word eddy. Suppose there is a quiet surface of water. You drop a stone in it. What will happen? Around the stone, circular waves are created, ripples are created. We call them as the eddies. So here also the currents are in the closed path. They are circulating currents. That is why they are called as the eddy currents. So if you take a thick conductor, the induced currents are circulating currents, and these circulating currents we call them as the eddy currents. So what is the definition of eddy currents? These are the currents induced in a thick conductor. This word thick is very important. Thick conductor. So to induce current, what should change? There should be change in magnetic flux. So whenever the magnetic flux linked with it changes. So these currents are called as induced currents. So this is the definition of the eddy currents. So what are eddy currents? Currents induced in a thick conductor when the magnetic flux linked with it changes. These are always circulating currents. They move in the closed paths. Therefore, they are called as the eddy currents. Now, how to change the magnetic flux linked with this thick metal plate? For that, we shall take the simple experiment which we had done last time, that is simple pendulum experiment. So, in simple pendulum experiment, you had a metal bob suspended by a spring and used to make it to oscillate. Now, let us remove the bob and connect this metal plate, thick metal plate, to the end of the string. And you make it to oscillate in the magnetic field. How do you get the magnetic field? Take two pole pieces of a magnet, north pole and south pole. Between them there will be a magnetic field. This is indicated by these magnetic lines of force. So there is a magnetic field between the pole pieces of a magnet and you make the plate to oscillate in this magnetic field. What will happen? When the plate oscillates in the magnetic field, then the flux linked with the plate changes and thereby eddy currents are induced in it. So this is an example which will demonstrate this eddy currents. So what is the example? A thick metal plate is made to oscillate in a magnetic field. The flux linked with it changes because of the oscillations and thereby eddy currents are induced in the plate. Now you had seen in Lentz's law, the induced current always oppose the change in flux. Right? That is, here the motion of the magnet is responsible for the change in flux. So the induced current oppose the motion. So here also the current induced in the plate, they oppose the oscillations. Therefore, the plate comes to rest very quickly. Right? Because the induced currents oppose the motion of the plate. So this experiment demonstrates the eddy currents. Now, what is the disadvantage of eddy currents? It has got a major disadvantage. You all know that metals are good conductors of electricity. So for a metal, resistance is very small. If the resistance is very small, the current flowing through it will be very large. Resistance means what? Opposition to current. If the opposition is very small, current can easily flow through it. So for a metallic conductor, there is a small resistance and the current will be very large. In the current electricity, you have studied the expression for power. Power is given by I square R. So for this, resistance is small, current is large. So if the current is large, what will happen? A large amount of energy is wasted in the form of heat. So when you must have observed, whenever a large current flows through a conductor, it becomes heated. That is, electrical energy is wasted in the form of heat. So here also the energy is wasted in the form of heat, and this is the main disadvantage of eddy current. There is loss of energy in the form of heat. Now, if you want to reduce the loss, this metal sheet is divided into a number of small sheets. It is cut into a number of thin sheets, and these thin sheets are joined together by insulating material. So it is called as a laminated core. So when it becomes laminated, then the eddy current loss can be reduced. Otherwise, there will be a large loss in current in the form of heat. Now, this is the disadvantage. Now, where do you use the eddy currents? Now, just now I told you there is a large heat produced by the eddy currents. This heat produced by the eddy currents, it is used in the induction furnace. So, in the induction furnace, what is done is the heat produced by the eddy currents, it can even melt the metals and it can produce alloys. So this is used in the induction furnace to produce alloys. Also, you must have seen the electrical power meters in your house. So in the electric power meter, there is a metal disc rotating at a constant speed. A shiny metal disc rotates. This metal disc rotates because of what currents? Because of the eddy currents. So they are used in the electrical power meters. Another interesting use of eddy currents is it is used as magnetic brakes in electric trains. So in electric trains, what happens? the wheels of the train, suppose this is the wheel of the train, there is an electromagnet fixed above this wheel. So if now the wheels of the train will be rotating in a particular direction, the train will be moving. Suppose you want to stop the train, what is done? Current is passed through the electromagnet. When current is passed through the electromagnet, magnetic field will be created and the wheels will be rotating in the magnetic field. Therefore flux changes and eddy currents are induced in it, and these eddy currents will stop the motion of the wheels. So therefore the train comes to rest. So it is used in the magnetic brakes of electric trains. Like this, many interesting uses are there for eddy currents. I have taken 3 uses. So what are the 3 uses? First one, it is used in the magnetic brakes of electric trains. It is used in the induction furnace, and it is used in the electric power meter. So these are the advantages or applications of eddy currents. So what are the 3 points we have done today for eddy currents? First one is the definition of eddy current. Second point is the disadvantage of eddy current. Third point is the advantage or applications of eddy currents. So let us summarize what we have done today. Let us define first what are eddy currents. These are the currents, circulating currents induced in a very thick conductor when the flux linked with it changes. These circulating currents are called as the eddy currents. What is the disadvantage? Induced current is very large because resistance is small. Therefore, a large amount of electrical energy is wasted in the form of heat. So, it generates heat. So, that is the disadvantage of eddy current. What are the advantages? 3 advantages I told you. It is used in the magnetic braking system of electric trains. It is used in the induction furnace, and it is also used in the electric power meter. So these are 3 applications of eddy currents. So these questions are asked for 1 and 2 marks in your exam. All the 3 questions are important. Definition, disadvantages and advantages. So in today's session, what points we have covered? In the first part, we have considered the motional EMF. That is, we have defined motional EMF and derived an expression for it. And for eddy currents, we have taken 3 points: definition of eddy currents, disadvantages and advantages. So this is all for today's session. Thank you.